One, go.
So hello, everybody. My name is Sam Pickholtz. I am the Vice President of Team 846 in San Jose, California. I'm here to do a presentation on spring counterbalancing of gravity arms. So just, any arm rotating mechanism on a robot. And I'm here to convince you why you really should put this on your robot, because spring counterbalancing does take a little bit of work, but the advantages are pretty significant for actually getting stuff working on your robot. So if you want to follow along on the slides, tinyurl.com/WVROC balance slides, you can see them. So yeah, might be fun to follow along. But what is counterbalancing? That's really the question that I'm trying to answer, as well as, why you should do it. So the goal of counterbalancing is to get rid of the torque that you need to lift an arm. So, you have a heavy arm and you want to go, lift it super quickly. How do you do that? You counterbalance it. Now, there are a few ways to counterbalance it. You can counterweight, which is dropping a big weight on the other end of your arm. It works, but let's look at what a counterweight actually is. It's a big weight on your robot and it's high up. And big weights aren't great on your robot because, we all get pretty close to the weight limit and that's never fun. And it's also pretty high up. High up weights, high center of gravity doesn't work very well. So while it does accomplish the purpose of getting rid of the torque you need to lift an arm, it doesn't do it well. Springs, on the other hand, are much lighter. They can be smaller. You can, of course, get giant springs. But it does take a little bit of work to set up the spring on your robot to counterbalance. But I'm going to walk you through how to set it up, what the advantages are. Hopefully you've learned something. There is a little bit of math involved, but it's pretty interesting if I do say so myself. But I'm also presenting on this, so maybe a little biased. But counterbalance benefits. The first thing is stuff goes faster, as I mentioned. If you perfectly counterbalance an arm, you only need to accelerate against the mass of the thing. So, I'm pushing, all of the force of the actuator goes into lifting the arm. None of it goes into pushing against gravity. Simpler and lighter powering mechanisms. So let's say I have an arm that's powered by a motor. I might need 3 motors just to hold the arm horizontal. But if I counterbalance it, suddenly one motor is just good enough. I mean, not only just good enough, but one motor is plenty. The last one is symmetrical movement, and this one is something that I don't think is appreciated enough as far as the advantages of counterbalancing. And by what I mean by symmetrical is if you have an arm that's going up and down, if you have the same actuator, so let's say a pneumatic that pushes it down and then pulls it back up, it'll go the same speed down and up. And why this is advantageous is because without counterbalancing, your arm will drop down super quickly and rock your robot and then take forever to lift back up. And ultimately, that just isn't a situation you want. Rocking around a really heavy arm on your robot just doesn't work too great. So by counterbalancing it, you can get rid of those problems. So a quick physics refresher: Hooke's law, springs follow it. All of these springs are going to be Hooke's springs that follow Hooke's law. So the force is negative kx. K is the spring constant. X is the stretch length. Springs store potential energy. Torque is a cross product in vector form. It's essentially vector multiplication, kind of. So, if you have 2 vectors here, vector A and vector B, the cross product is going to be perpendicular to both, and the magnitude of that vector is going to be the magnitude of vector A times the magnitude of vector V times sine of the angle in between. So with torque, you have the radius of the arm times the force that you're applying times sine of the angle in between, and that will give you the magnitude of the torque. So torque of an arm due to gravity is the radius to the CG of the arm from the pivot point, and then the weight of the arm, which is the force. So if you have an arm, the maximum torque is when the arm is horizontal, which is going to be the radius times the force of the arm. So that's pretty straightforward stuff. Energy of an arm is just the change in potential energy of the arm as it goes up and down. So the energy is going to be force times distance. The distance moved is going to be the vertical change in the center of gravity. And the energy is just going to be the multiple of those two. So now we're getting into counterbalancing. That's all of the intro to physics stuff. So counterbalancing, what if we could pull off a perfect counterbalance? That's really the question I'm trying to ask. Like, perfectly, the torque of the arm due to gravity is counterbalanced by one single spring. Do you think that's possible? Well, I mean, I guess it kind of is, but let's look at, we're trying to counterbalance an arm which has torque due to gravity. We're trying to get rid of that torque due to gravity. What can we use to get that? We're using a spring as the name of the talk implies. So do we put a common spring somewhere on the arm? We could also put a torsion spring at the base, but will these perfectly counterbalance the arm? So what do we really need to figure this out? We have the torque of the arm due to gravity, which we went over previously. We have the torque of the spring on the arm, which is made up of components, of Hooke's law. You have the force of the spring, and then you have the radius that it acts upon. And then you have the stretch length of the spring and the spring constant, which make up Hooke's law, which give you the force, which give you the torque. So if we start at the top, the torque of the arm, torque is going to be the radius cross the force. So we want it in terms of this angle, theta. So you'll notice that because the vertical support here in yellow is parallel to the downward force of gravity, these angles theta are going to be the same. So you can just do the radius of the center of gravity times the weight of the arm times sine of theta, or the torque at 90 degrees when the arm is horizontal is going to be the radius cross the weight, or radius from the pivot point to the center of gravity. So now we have the first step in it, but let's move on to the next step. So here we want to solve from the bottom up. So first finding the spring constant, then the stretch length, and the force, then the torque. I mean, the spring constant, we can just keep it as K because I have no idea what it is. You don't know until you figure out exactly what spring you're going to use. But generically, you can figure out the spring stretch using vector subtraction. So you could do trigonometry here, but vector subtraction yields a really nice result. So vector subtraction, if you have a vector b starting at the pivot point going vertically, a distance of h in the y direction, and then a vector a going horizontally-ish along the arm, a distance of r. So r is the vector of the arm, and r is the distance to point A. Then vector subtraction of b minus a will yield a vector pointing from A to B. And the magnitude of that vector we'll call the stretch of the spring, if you have a spring stretching from point A to point B. Now, this gives us the spring constant, the stretch length, and using that we can find the torque on the arm, as long as we know what this capital R value is. So from here, we have everything we need, so we just need to solve it. So this is the actual counterbalancing math. So the counterbalancing math, there are a few ways to do it. This first step is using geometry. So if you remember, the cross product is going to be the one vector magnitude times other vector magnitude times sine of the angle in between. And that's actually the area of the parallelogram between the two vectors. So you can solve it that way. You can also use trigonometry to solve it by using the law of sines to find this length and then doing a cross product with that. Or you can use it the vector way, which I think is the nicest. Ignore the distortion from all the converting from a PowerPoint to a Google slide. But anyway, so you have the torque is going to be a radius cross force, or in this case, a radius cross the spring constant times the stretch length. And S is going to be H minus R. I had B minus A, but it's the same idea. So you have R, the vector R, which is here, cross, which is the radius that the force is applied, cross the stretch length of the spring, right? So this, you can factor out the spring constant and you get R cross H minus the spring constant and R cross R. Now, R and R are the same vectors, and sine of 0 is 0. So sine of 0 is 0, so you can cancel that out entirely, and you get an answer. This is a typo here, but it's KRH sine theta. And now what's very significant about this is that the torque of the arm due to gravity is also a function of only sine theta. So here you have a constant in K, a constant in R, and an equation in sine of theta. And the torque of the arm is going to be the radius of the arm and then the weight of the arm times sine of theta. I see somebody saying, "What do you mean?" in the chat. Oh, that's somebody else. Okay, never mind. So using this setup where you have a spring that stretches exactly from one vertical support to some point on the arm, as long as you get KR squared to be equal to the length of the arm times the force of the arm, then you can perfectly counterbalance basically any rotational arm on your robot. Um, so, I mean, the advantages going back to the previous statement are pretty significant, but there are also some challenges here. Like you need a spring to stretch exactly a distance between 2 points. So when this arm is all the way up, the spring has to be at 0 stretch length. And nobody yet has made a spring that can start at 0 length and stretch to something. They all start at a length and stretch by something. So how do you get around this? Well, there are a few ways, but the easiest is just to put a pulley at one of these endpoints. If you put a pulley on this point, for example, then you can stretch a rope or piece of string from this point along this length and then put your spring somewhere up here on the arm or down here on the arm or somewhere else. If you attach a rope there, put it around a pulley here, then you can attach the spring somewhere, on the rest of your robot and perfectly counterbalance it. Now, here you can see, this is what I was talking about, where you have the torque of the spring is kr squared sine theta, and the torque of the arm is going to be Lw sine theta. And because they both follow sine theta for any value of theta, as long as the constants are the same, then the arm will be perfectly balanced. So here's a representation of what it would look like in application. You have your R and H when the arm is vertical and a tiny bit of stretch between these 2 points. So your spring is going to be basically relaxed at this point. But as your arm moves outward, your spring is going to stretch by a certain amount until your arm is at your ending point, which in this case is horizontal. If you go past 90 degrees of rotation, you can do it, but you need really long spring lengths because otherwise you're going to be pulling a spring to like 4 times its initial length. Now, one other addition to this is you'll notice that with this equation, we need a very precise value of K. And that's hard to get. You can buy a spring with a certain value for K, but the torque of the arm is already set by your design. And the radius is a value that you just, you can calculate a value of R to make it work with this equation. But K, you can buy a spring with a certain spring constant, but sometimes you can't find a spring that's a spring constant you want. And how you can get around this is with surgical tubing. So latex surgical tubing, a lot of teams use it on their robots for counterbalancing, maybe not perfect counterbalancing though. And the reason why it's special is because you can cut it to any length you want. So if you take a spring that's, let's say, 10 inches long, that provides 10 pounds of force per inch of stretch, and you cut it in half, now it's going to provide 20 pounds of force per inch stretch because it's going to provide a force based off of the percentage that you've stretched it, not the actual distance. Somebody said this is a neat, legitimate use of physics in FRC. Yeah, so you can overspec and it'll probably work. I'll get on to, at the end of this, why this is a much more elegant solution to actually doing it. Why I see here variables like kr and kxr. What's the difference? So this, as I was saying, there's an error that I messed up, and this is kr squared, but it can be krh. Essentially, it's just the distance here and then the distance here. Somebody asked me to go back a few slides, I guess. Are you talking about this one? Yeah, so you can see here the R and H, which are supposed to be the values R and H, get converted to R squared. So that's the mistake. I have a note down there, but so I mean but theoretically you can use any values of R and H. Just say your H is a value of 6 and your R is a value of 4. Your spring, when the arm is vertical, is going to be 2 inches long, so it's already stretched. But because R and H have no angle in between them, you're providing no torque, and it's still perfectly counterbalancing. So yeah, you can get into equations of elongation. So I'm not going to get into this specifically, but you can look at the slides at the end, and if there's any questions about how to actually set up or calculate the lengths of the springs that you want to get counterbalancing to work, I can go into that. So this is just an example of how to do it. Here are overall equations. An interesting note is you can do it with surgical tubing, and these are all of the equations you need to do it with surgical tubing. So you have your value. This gives you the radius with a set input values from your arm. This gives you the spring constant that you can calculate out in a few different ways depending on what your constraints are and what you have flexible. And then from there, you can calculate the lengths of your springs to figure out if you have enough room in your design to get it to fit. But it can also work with a torsion spring. So if you take a torsion spring, attach it to a spool with rope going around it, then you can counterbalance as well. So in this case, there you have to do slightly different equations. You start at a certain theta value, you have a certain amount of travel on your torsion spring. Okay, so I'm seeing question 4RH. So again, R is the distance from, it's 4 times R times H. So 4 is just value 4. R is going to be the distance from your pivot point to where your spring is attached on the arm, and H is the distance from the pivot point to where your spring is attached on a vertical support. That only works when R and H are the same, and you can actually see it's just a restatement of these two other radius of spool equations above. So if you multiply these together, you actually get this equation when R and H are the same. Otherwise, it gets more messy. So this is another way to do it. Say you have limited linear space in your robot because a spring will stretch linearly. If you have limited linear space in your robot, then you can use a torsion spring and it will unroll rotationally and get you more space. But you do need to find the right torsion spring to use. Yeah, my notation is not too consistent. Sorry about that, but I mean, variables are going to be one letter long, unless they're subscript. Then that's information about like where they're applicable. So theta minimum is the minimum rotation of the torsion spring because sometimes you start with a preload, and then theta maximum is the maximum rotation when your arm is at the end of travel. Yeah, sorry about my notation. It's a little bad, but I hope the point is getting across that you can do it in a lot of ways. I didn't include the math here, but you can also do it when you have a set spring constant and a set max travel on your spring, and that's what you have when you have a caught spring, and you can apply that to a similar situation. So this is the torsion spring counterbalancing, but there's another type of spring that I thought would be fun to get into that's used a lot. Most notably, I think the best done I've ever seen it is 254's 2019 robot. I don't know if this is mostly East Coast teams, but you probably know the Cheesy Poofs 254. They had a giant arm on their 2019 robot that was counterbalanced with a gas spring, and it was the cleanest design I've ever seen. But I guess first I should give context on what a gas spring actually is. So a gas spring is a lot like a pneumatic cylinder, except for it's sealed. And there's a lot of nuances that go into it that I completely don't understand. But the general idea is that you have a plunger in the center with holes in it and equal pressure on both sides. So you usually have a crazy amount of pressure, so 1500 to 2500 psi in these. And what happens is on one side, you have the full area of the bore to push up against to provide outward force on the gas spring. But on the other side, you have the area of the bore minus the area of this output shaft. And that, if you set it up your gas spring right, is a significant enough difference in force on either side that you can get 20, 30, maybe even 100 pounds of force out on your gas spring. So they provide almost constant force. They do have a rise. I see somebody, is this VOD? I guess that is the slides. I have a tiny URL to the slides that I can show you again at the end. But so gas springs will typically rise in force by a little bit as they go through their travel. Another significant thing is they have damping. So if you instantly provide a force, they'll kind of go in a little bit and damp it, because my understanding of this, the very high level understanding, is because it has to force the air through the tiny holes in the piston, but take it with a grain of salt. This is actually from gas spring manufacturer, and you can see all the nuance here. They actually have a hydraulic acting period and then a pneumatic acting period. So they have different forces. I guess from reading their website, it sounds like the oil inside of the gas spring does some fancy stuff, but a good enough model is just take the force that the manufacturer provides or McMaster provides and say, it's constant and go with that. That generally is good enough once you include friction and any other outlying factors. So how do you actually use a gas spring to counterbalance though? Well, it's a lot like if you've ever done a pneumatic powered arm. So you might recognize this simple geometry thing if you've done a pneumatic powered arm. If your pneumatic anchored at one point back here along a post somewhere, and then your arm is going to be this dotted line through its range of travel. So this is the starting, and this is its ending, and going over a certain travel angle. And you have different variables. You have the retracted length of your pneumatic, the extended length of your pneumatic. You have an initial angle here and a final angle, as well as the radius your pneumatic is mounted and the center to center distance between your end point of your gas spring and this attachment point onto the pivot point of your arm. Right? Has anybody seen something like this before or done pneumatic powered arms? So the question here is, you have the geometry, but you want to figure out how to actually apply that geometry to counterbalancing. Of course, an arm has torque, so how do you calculate the torque? So you want to find the torque relative to the center distance, the force of the pneumatic, or in this case, a gas spring, the radius of the pneumatic attachment, that's this value here along the circle, and then A is the angle from this x-axis to wherever the pneumatic position is, and then L is just going to be the generic distance of the pneumatic at any angle A. So you can kind of probably see how you would calculate this. So you have a certain torque is, of course, a radius cross a force, right? So you have your radius here in R, and you have your force here in F. But you also need sine of the angle in between, which in this case is alpha. So how do you find alpha when at any given point, like when you design your system, you know your initial angle here, you know your travel angle of your arm, but you don't know what alpha is necessarily at any point given an initial angle value. So how you can get this value is just doing a bunch of trig bashing. It's kind of annoying to do, but it works. So what you do is you do the law of cosines to find this value of law of cosines of R and C to find the value of the length of the gas spring or pneumatic at any given angle A. And then you do the law of sines to get the value of this angle, alpha, and then do a cross product with that. So this long equation gives you the torque of the gas spring or pneumatic on the arm at any point. Are there any questions about this? I can move on, but if anybody brings up any questions, then I'm happy to answer. So a few design notes here. Of course, the initial angle can't be less than 0, and the travel angle can't be greater than 180, because then you're dealing with an overcenter mechanism. Now you can design intentional overcenter mechanisms, but in this case, we want bidirectional motion. And the max torque also comes when alpha is closest to 90 degrees, because that's when sine is closest to 1. So if you're designing an arm with a pneumatic powered arm, you want to do your best to design it so that when the arm is horizontal, alpha is close to 90 degrees. That will give you the most amount of force or the most amount of torque when you need it the most. So now you get, previously we had a perfectly counterbalanced arm by definition. Like we had a spring that provided exactly the torque of the arm at all points. But in this case, this equation here isn't a function of purely sine of theta. Theta is almost no relation to alpha. Like they scale linearly, I guess. Like if theta gets +1, then alpha gets +1. But alpha doesn't necessarily have to be related to theta as far as its actual value. And then you have all of these square roots and squares and all of the addition and subtraction, which it just doesn't work out. Actually, I tried to map them out, and you can approximate as best you can, but it's never going to be perfect. So how do you actually make sure that you can power your arm and lift it up properly? The best way I found an answer to is just graph it out. You can graph out the torque of your arm, which is this bottom red value here. And then you have the torque of the moving force, which is the pneumatic force or the pneumatic torque, and then the gas spring torque as well. Math, I think, yes. It's all just a bunch of math. But if you plan this out, you can do some pretty powerful things with light pneumatics and, heavy arms. Um, so calculating the Zoomy Zoom, this is my abbreviation for calculating how fast it's actually going to lift. Because, I mean, we're already doing all this math. We already calculated out exactly how we're going to counterbalance it. We want to know a little more information. So, one of the benefits of counterbalancing, perfectly at least, is theoretically, now you can have the tiniest little pneumatic and it will lift your arm all the way. But you don't want to be sitting there for 10 seconds waiting for your arm to lift. You know, that's what is it, a 13th of your match already gone by waiting for one movement of your intake. That's no fun. So you want to calculate how fast it's actually going to lift the arm with a given pneumatic. Uh, so the first equation that comes to mind is we have the torque of the pneumatic, and this equation, T equals I alpha, where I is the moment of inertia of the arm, and alpha is the angular acceleration. Angular acceleration is in terms of time. We can just integrate twice and we're done. But our torque is not in terms of time like angular acceleration, it's in terms of theta. So to the rescue is, I'm going to call it time step analysis. I don't really know the formal term. That's what I remember somebody calling it. The idea of just going through very small periods of time and calculating out what approximately happens during that period of time. So we can take our initial pneumatic angle, which is just from our design. We can just take that directly off of whatever CAD application or CAD software we're using, or you can calculate it in other ways. And we can calculate the torque using the equations we've had previously. And if we have the torque and we have the moment of inertia of the arm, then we can use T equals I alpha to find the angular acceleration at this time. Then we can integrate to find the angular velocity at the end. I did the end of that time period, the angular velocity. Then we can find the number of the radians traveled during that time period, add it to the pneumatic angle initially, and increment the time by one, in this case, 1/100th of a second. And what you'll end up with is this, we're starting with the arm horizontal and we need to travel, in this case, 83 degrees or something, because that's what this design required. And we graphed out, it takes about 0.4 seconds to lift. So this was for these calculations are for Team 846's 2019 robot. So that arm, I'm going to get into the specifications, but there's 83 degrees of travel. It was, I think, about 15 pounds. And I was using two 3/4 inch pneumatics, which are, relatively big, but nothing close to what I've seen other teams use. And it was able to lift the arm faster than we knew what to deal with. We were almost putting flow limiters on the arm just to get it to not rock our robot around completely when it lifted up and down. And it's all because we had one spring that counterbalanced the arm perfectly. So gas spring is, I'm going to go over the basic idea, is it looks amazing. Like, even if you use spring counterbalancing and use a bunch of special tools to attach the spring really nicely to your arm, it takes up space. But gas springs, you can mount them directly to the arm and they're super clean, but they're not perfect counterbalancing. So, you don't get that symmetrical motion. So if you overbalance it when the arm is going up, your pneumatic or whatever's powering the arm is going to have to push against that overbalancing to push the arm back down. Meaning that you can get it really fast going up, but slow going down. And if you underbalance, it's going to be slow going up and fast going down. There's no way to get it to be even, or you can approximate and get it as close as possible, but that's as best as you can do. And also, it's basically pneumatic setup. So if you have a pneumatic powered arm and then a gas spring, you basically just have two pneumatics pointing in opposite directions, or you can even have them pointing in the same direction, I guess, if you have a pneumatic pushing from the bottom. So yeah, I kind of wanted to get to an interesting point of graphing the power of counterbalancing, because I went over two different forms of counterbalancing, which, in theory, they sound great. Woo, we can lift our arms faster, and we can do it cleaner with, less required to actually lift them. But how much better are they actually? And I'm going by the time scale, measuring the difference in time approximately. So for this case, I'm using our 2019 intake, which is this big monstrosity. It was 14.5 pounds, so a little less than 15, almost a foot from the pivot point to the center of gravity, and at a 93.85 degree range of travel. Don't ask about that range of travel. That's a whole other mess. But, if you wanted to lift this with a gearbox, you would have to have the gearbox would be heavy, and you would have to have something like a 501, 401 reduction on your 775 because you want to get it from 18,000 RPM down to 1,000 RPM, or not 1,000, 1 RPM or something like that. Maybe not 160 RPM or something, which requires a pretty significant gear reduction, which requires a larger gearbox. And if you use a versaplanetary, then you're using the tiny Tenda ones, and they break and don't carry the load. And if you drive into something, they break. Um, and if you just plainly use pneumatics, you have to use some pretty big pneumatics. So calculating it out, here is the force of the pneumatic, or the torque of the pneumatic, in this blue line. And here is the torque of the arm in this red line, significantly higher than the other. So you have a decent bit more. It looks like about 150 inch-pounds more torque from your pneumatic than your arm requires to lift. And it still takes 0.5, I don't know, 3 seconds. And that's with a 1 16th inch bore pneumatic. So that's two of them technically, one on either side of your mechanism. So that's two pretty big pneumatics. Now, with the exact same pneumatic geometry and adding in a little bit of gas spring geometry, we can get that time a little bit shorter, but by going all the way down to 3/4 inch bore pneumatics, which on the grand scheme of things, it's not that much smaller in diameter. But if you're talking about actuating your intake, I don't know how many times you would do it. Maybe let's say you go to pick up a ball, miss it, pick up your intake, go again. A smaller pneumatic means that you use less air, which has less strain on your compressor, which overall is a much better situation to be in. So, it's not too much faster in this case, but it is a more optimal situation, I would say, from a actual usability standpoint. And now, of course, as I mentioned earlier, you could make it so that this gas spring had way more torque than the actual arm. So here's the arm torque, and you could make the gas spring have from 150 inch-pounds and go just up to a crazy amount of torque on the arm. But then when you push the arm back down, you have to push against that. So it's going to go really fast up and really slow down. So in this case, I have the gas spring underbalancing slightly. And so that means it's going to go slightly faster than this down, but it's still going to take half a second to go back up. So now we can look at perfect counterbalancing. So this is almost copied over from previously. It's using the same geometry for the pneumatic, same 2 3/4 inch pneumatics, same exact arm, but now just adding in a perfect counterbalancing system, and it's 4/5 of the time. And that's just because that 1/5 of error comes just from this error between the counterbalancing and the moving force. So by getting the arm perfectly counterbalanced, you're wasting no torque moving it. Like, you're wasting no energy to push against what you're using to already lift it up when you're pushing it back down. Which, in actuality, will this be, will you stave 4/5 of the time, and is 0.1 seconds really that significant? Maybe not. I mean, it depends on how much you're using your intake, or, how heavy your arm is, and a bunch of other factors. Like if you have a bunch of friction in your mechanism, this is negligible. This difference is just going to disappear because of that friction. But in an ideal case, you can just see the immediate advantage of counterbalancing perfectly. Now, that's not to say you could improve the gas spring geometry to get it closer to this. I just drew this up and approximated the gas spring as quick as I could, 10 minutes of fudging around with numbers, and I got it to graphically approximate. But overall, it's just much more effective to directly counterbalance. So are there any questions about anything I've discussed so far? I am not seeing any. Okay, well, is there anything you want me to go back over? I guess I can show, not really, it seems. Well, if you want to look at it, I made a video with one of my other teammates about this. So if you're looking back over and you want to see cool animated graphics done by not me and another person on our team who actually knows how to do that, but if you want to see the math of the spring counterbalancing in action, you can go to this tiny URL and you can see it. And if you want to look at these slides over to look at all of the equations I posted, then you can go to this link or this tiny URL and you can see all of the equations and write them down. Yeah, cloned cheese. Really? That's your username? Okay then. Yeah, so I have, yeah, shout out to that guy for the fancy animations. They're actually pretty impressive. I mean, I'm no expert, but I thought they were. So going back to the information that I skipped about the actual application of the surgical tube counterbalancing, when you apply counterbalancing to the real world, you have a certain inner diameter and outer diameter of the surgical tubing, and that those values are going to give you the amount of force you get based on the percentage stretch. And using that, you can use these equations here. So if you have the force at a certain stretch percentage, in this case 100%, and you divide it by the initial length of the spring, then you can get the spring constant of that section of the surgical tubing. Alternatively, if you have the force at 200% and you divide it by 2 times the initial length, then you'll get the spring constant as well. That sort of thing. You can also do that's what this says here. The force at 100% times the stretch percentage over the length of stretch will give you the spring constant as well. So what you can do then is you can apply it to this. So if you see H is going to be the overall, so where should I go here? Yeah, this slide first. So the relaxed spring is going to have some length. Let's call it L0. And as it stretches out for an arm that's going 90 degrees, the maximum distance is going to stretch if R and R down here is going to be this distance, which is R square root of 2 right there. So the maximum distance is going to stretch is going to be L0 plus the R square root of 2, which is the elongation times the initial length. That weird E is going to be the elongation. And then to calculate the overall length, you can get H is going to be equal to L0 plus the elongation times the initial length plus R. So you're going to get L0 and then plus that value. And so then the initial length is going to be equal to, going back to this previous equation, you can solve for this initial length. So you have the initial length is R root 2 over the elongation. And plugging that in, you can solve for how much physical space in your design you need to accommodate the actual counterbalancing of your arm. Yeah, so I'll just go over these slides. The max elongation for latex rubber between 100 and 200%, so that's stretching it from, let's say, 3 inches to between 3 and 6 inches. Once you go past that, it's no longer follows, Hooke's law that well. It starts getting all weird and, increasing in force really rapidly as you stress the material a lot. And then, so once you have your elongation, you can calculate R based on the elongation. So here you can see you have R based off of elongation, which is the stretch percentage, and the force of the spring, and H and the torque of the arm. And then from there, in application, you can calculate the maximum spring force from the energy. So one notable thing is that springs store energy. Of course, they store potential energy in 1/2 kx squared. It's just the integral of force. Yeah, it's the integral of the force. So that the actual maximum spring force is going to be based off of that. Um, and if you do your counterbalancing right, a nice check is that the force of the spring, or the energy of the spring over its motion, is going to be exactly equal to the change in potential energy of the arm. Exactly. And that's a good sign that you did all your calculations correctly ahead of time. Then you can select your latex rubber that is close enough, and then you can iterate through it and recalculate. I got rid of the iterating with my calculations. You can do it all in one step. But if you're doing it by hand, then you need to iterate. So this is a simple example. You can find the maximum length, the radius that you can choose, and then calculate the overall length, and you can choose your spring and calculate out what the length of the rubber will be, cut a section of the spring to that length, and then attach it to your arm. You're off to the races, essentially. Yeah. So that was the information about counterbalancing that I have here. Are there any questions that, or things that people want me to go over now that have covered a little bit more of it? No questions. Okay, then. Can we get the slides? Okay, I'll go back to all the way back to the start with there. So it's tinyurl.com/WVROC balance slides. Yeah, linked there. So this should be enough to actually go off and try to counterbalance. Yeah, so to actually go off and counterbalance an arm on your robot, it's quite flexible. The spring counterbalancing, gas spring counterbalancing, same. You can counterbalance almost any arm, and there are nice workarounds to get the space that you need. You can, if you have the spring and you don't have a straight length long enough to counterbalance in one location of your robot, just get a really long piece of rope and stretch it around a bunch of pulleys and get your spring to a location where it can stretch out and work its magic with counterbalancing. So yeah. That is counterbalancing. I hope to see a lot more teams using counterbalancing in their virtual designed robots that are definitely going to be built by the time semi-build season rolls around. So yeah. I guess more counterbalancing, because counterbalancing is great. You can also, something that I know a number of teams do this, but counterbalancing lifts, if you do it nicely, it can be great. I have a question here. Can you talk a bit about how you used methods like this in your robot? I'd honestly just love to know about your robot design in general. So if I can pull up a different screen, I can show that. So the website, what is it? Wait, Lynbrook Robotics. LynbrookRobotics.com, our robots. So my rookie year was 2018. So here you can see our 2018 robot, and you can see the climber over here in the graph. So how we designed our climbers, we had a winch at the bottom, rope going up, and then we had this long swinging arm with a hook at the top that would swing up onto the bar. If you remember, yeah, so if you remember the 2018 game, there was a little bar and you wanted to climb onto it and you had to lift your robot a foot off the ground, but the bar was a decent bit taller than the rest of our robot. We had to lift, but we were using a cascading design, so if we brought our lift up, our intake would get in the way of putting a hook directly on, and we didn't want to trust our lift to be robust enough to lift the robot. So we're going to use rope going through a separate hook. And to get this really, this is the part I designed as a freshman. You can see my name right there. Is if we wanted to get this really long arm up, but with an arm that long, even if you have a really light hook, there's a decent bit of load on it, and we don't want to have giant pneumatics just to do this simple job. And we already have a really long arm, so I counterbalanced it by putting the spring on the arm, wrapping it around a series of pulleys. I had to get off with 2 pulleys instead of just 1 to reroute it, because otherwise it would disconnect with the pulley, because I had over 180 degrees of travel on this arm. But by doing that, we could use, I think I had like 5/16 pneumatics on either side, some absurdly small pneumatic that realistically can't do very much, but once you counterbalance it, it lifted up plenty fast. I guess it's loading something. Yeah, so then we have our 2014 robot. This was, there's no image here except for this little image. Oh, I need to scroll now. Okay, our 2014 robot. So this is when our head mentor kind of discovered this. There is one paper I found on this style of counterbalancing. But we had a big intake, didn't want to have a giant gearbox or really big pneumatics. So we have a spring counterbalancing system that counterbalances the intake as it moves up and down. And the geometry and calculations for this setup was done at that time in 2014 by your head mentor. And then the example I was using just now, can you show the link at the end again? Yeah, 1 second. It is tinyurl.com/WVROC, or I think, did I misspell it? It's ROX, I'm pretty sure, but I misspelled it. Whatever, that should work. Other is balancing video, yeah. The balancing video is these. I have 1 ROX, 1 ROC, wonderful. I'm very consistent, just like my notation. So, yeah. But this snippet here, which I pulled off of our robot for the intake, our intake was counterbalanced as well. 15 pounds, our robot was, what was it, 120 at the time. So that's a sizable portion of our overall robot weight that is moving up and down on our lift and pivoting up and down. So we didn't really want to have, 3-inch bore pneumatics lifting this up and down. That's a huge amount of air you're wasting, and I already had experience with counterbalancing, so I made it work. One thing that's underappreciated, or I mean, it's appreciated once you realize it, but if you counterbalance an arm properly, you can put it in any position and it'll just sit there. And there's an example of that in the video. The 2018 climber part, you could just put it at any angle and it'll just rest there. And if you push it, it'll slowly glide to a stop due to friction. No matter if you push it up or down, as long as you push it with the same force, it'll glide roughly the same distance and slowly glide to a stop. It's pretty fun to play with. Plenty of people were hit in the head while playing with these counterbalancing mechanisms. So yeah, counterbalance safely though. Yeah, so that's how it's been used on a robot. We didn't put any of it in our current or last year's 2020 robot. I see another message. Your graphic is really cool. Yes, so this was done by one of the graduated members of our team, now an alumni, but very good at graphic design and stuff. And you just render in all of the mechanisms, and then we put this in a book to talk about, the different portions of our robot and how they function. So, yeah. I have 10 more minutes left. So, are there any other questions that people have? Getting another. Yeah, so, I mean, I guess going back to takeaways for this. Counterbalancing is great. There are a billion benefits, maybe not quite a billion, but there are a significant number of benefits to doing it. And ultimately, it does take some work, but I feel like I hear plenty of I hear plenty of teams that I don't really know exactly how other teams work, but there are plenty of teams who just kind of cobble stuff together. And I feel like part of the problem is the wonderfulness of versaplanetary gearboxes. And you make an arm, you strap a versaplanetary to it, and oh no, it's going too fast, just increase the reduction. Oh no, it's going too slow, just decrease the reduction. When you can do a little bit of math ahead of time, practice your physics, and create something first try that works almost exactly how you wanted it to. And that's kind of what counterbalancing can do for you. If you apply it properly, any mechanism, no matter how big or how small, you can move around however you want and control to your liking, which is kind of the amazingness of it, to me at least. And you can apply this mathematical approach to robotics wherever you need. I did a bunch of math for the shooter this year. I was the designer for the shooter, so I ended up doing a bunch of trajectory analysis calculations and momentum transfers to get a set of equations that we could eventually give to software so that we could automatically set velocity, aim, and fire at a target almost immediately just from information from the limelight. We get the vision target, use that to calculate the distance to the target, and immediately we know we go through one calculation to find the shot velocity, one calculation to find the initial velocity of the rollers, then another to just find the velocity of the motor we want, or the motor velocity, and then we can shoot the ball once the motor's spun up. And then also a bunch of calculations to figure out actually, wait, can I show that? CAD 20, design documents, shooter. So these are the design documents that I was doing. So I do most of my calculations in Excel because it's convenient and wonderful and is totally intended for this style of purpose. But you can see all of these pages I did. So first doing trajectory optimization. So these are trajectory analysis equations. I went way overkill over here a little bit. This is minimum momentum, but the core idea is this equation, which gives you the initial velocity of the shot projectile given a distance to and a height of the target relative to your shooter position. Apparently the stream is frozen. So I see that now, yes. Oh, no, I think it's because I see what happened. I need to stop the share real quick and then share that. There we go. Did that work? I think it did. Coolio. So back in action. So this is a bunch of calculations, and you can, this is generally no knowledge about, in the y direction, a projectile of constant negative acceleration, and then you can go through that and find this equation, which is the velocity of the shot projectile. But that's the velocity of the projectile, not of your rollers. And it isn't just a simple conversion of surface speed of roller to launch velocity, because when the ball gets shot through the rollers, you have to impart momentum into the shot projectile. So I have to calculate out that momentum. So you can calculate out that momentum. I'm just talking for a little bit because I have a little bit left and I don't want to leave them hanging. But you can calculate out that momentum, and then you can take that information to, in real time, calculate how fast you actually need to spin your motors up to get a perfect shot. In theory, it worked meh in practice. Good enough. And then you can also do calculations here. So this is my proof that a two-angled hood will work with certain parameters on the shot quality. So velocity and entry angle, as long as they're within our parameters, I can select angles for what I want the two different shot angles to be at. And that allows me to have a 2-position hood instead of an infinite position hood. So I can use pneumatics instead of motors, which are a lot easier to design around. And then you can do, not that, here. Down below, this is the really cool part. There's this really complicated differential equation that is explained all throughout here that allows you to relate the torque of the motor to the load of the system and allows you to calculate out a recovery time for your shooter. Now, of course, there's electrical time, the duty cycle of your WVRO or whatever, it's not checking every single second, every millisecond or millionth of a second. So, this isn't a perfect amount by any means, but you can get a general idea, in this case, 0.163 seconds, that, if you double that, we're still, we can shoot balls pretty quickly. That's good enough for me. It isn't the exact actual value, but it's good enough for, rough guesstimates. So I guess, there are 4 minutes left, so I'll just see if there are any last questions. If you all got access to the slides, did you all get, anybody who still wants the link to the slides that doesn't have them? I guess not. So, thank you for showing up. I know that this was a very technical thing, and you were probably trying to get away from all of your math classes and physics classes for, playing some games on a live stream. But if we're talking about robotics, then this ends up, I think, being a pretty cool way of doing things. So, yeah.
Thanks for watching. If you want more fun content, be sure to subscribe and ring the bell to be notified about our latest videos. Thanks to all of our co-executive producers on Patreon and Tier 2 Plus subscribers on Twitch, keeping fun loud, live, and independent.